Okay, so my plan is to talk on the supplementing this morning talk, and also to after that I would like to talk to you that why operator algebra is operator algebra is a natural thing to consider in the general mathematical frame. Okay. This morning with that construction are, that's the problem here. Okay, let me write it very large. Is that compensate the poor visibility? X group G measure mu, non-singular transformation, you have it. Then you have the modular automorphism coming from the following, usually that the measure mu gives mu of f, which is integration of f of x, the mu of x over this. Okay. This is definitely a way on A. That's, this is A. Then the other factor R is the A crossed product by G. And phi is this dual weight relative to the measure mu. So this is what the control the model. And tell you what happens. Okay, now what is then M is R cross product by sigma phi relative to R. This is the core. Okay, this is the core. And is it possible to visualize this core N? Okay. I tell you, actually, the construction is very, very simple. In fact, it's the following. X tilde is R plus non-zero positive real times X. Now, I now go back to the notation change. GH is the element of G. RST are element of real line. And lambda, I don't think of mu. Mu is reserved for the measure, so this is 0 to plus infinity. Is it better? Okay. And so now, this is your new space. Over here, you act TSG for lambda x in the following way. Exponential s times rho of gx lambda and gx. Okay, now let's forget about the s. This is tilde. But I also write T tilde G, T tilde S. When there's no no couples appearing. Okay, so Ts tilde S is TSE. T tilde E, G means T0 G. Okay, so omitting that trivial element in the other side. Okay. Remember, we had this cocycle identity, very nice cocycle. Rho G H X, rho HX. And rho, by the way, Gx is the ratio of the G translation by G and untranslated. The Radon derivative. So let's examine how it goes. T tilde GH for lambda mu, or lambda x, equal to rho GH x and GH x. Okay. So this is rho G Hx times rho Hx and G Hx. Okay. Now, here is lambda. Here is lambda sitting. Okay. You look at this as a new point in the positive real line, and the G times Hx, G times Hx, that's the definition of the tilde G, you forget G, Gx, and translate lambda by rho Gx. So this is Tg. Tilde G acting on rho Hx lambda to Hx. And then this is by definition Th, that T tilde H. T tilde H of lambda and x. So very nicely behaving. You can't expect anything better. Okay. Now, if the miracle occurs when you integrate. So you take f positive function on x tilde, the pair of a positive real number and x. And here, measure we are talking is Lebesgue measure on this one, not multiplicative R measure. Okay, R plus the measure we are assigning is a Lebesgue measure. So it's not a hard measure of R plus star. So F Tg tilde of lambda x, yes, lambda x of d lambda d mu x. Okay, this is along the, okay. So this is first x and the first r plus star f of rho g x lambda g x and d lambda d mu x. Rho gx, this remember integration f of x dx, okay, with d lambda, the Lebesgue measure. This is 1 over a of f of lambda d lambda. That's a change of variable by this simple positive number multiplication. So this implies no. So we change order that the Fubini for positive function. So this goes to the outside, and still that's the rho g x inverse of f of lambda gx d lambda d mu. And now you take d mu one, there you get rho gx out, pop out. And so this cancels nicely. F of lambda x d lambda d mu x. With this one and the Radon derivative about the gx, the cancel. The integral of f of gx d mu of x equal to rho of gx inverse of fx d mu of x. That's the rho function, the rho. That, in other words, this t delta leaves measure mu tilde invariant. T delta G. The G portion leaves measure invariant. And Ts of lambda f d lambda is f of e to the minus, what is that? It was, we assigned es. Bs lambda x, d lambda d mu x. And yes, so it goes out e to the minus s f of lambda x d lambda d mu. So that means that the Ts is the scaling. So, but we are talking alpha sf of lambda x was f of e minus sx. So that means that if we do that, this becomes Ts inverse e minus e plus. So maybe you want to have it here e minus s, so that then we have that, and alpha s of s is e sub s lambda, and integration make it here minus s, and so es. So this measure of f circle Ts equal to es of mu of f. but we need theta S is the inverse, so then inverse. Okay, so this scalars, so mu hat is your trace tau of theta S. Okay, now what the claim is, the theorem is, maybe I should state now theorem for n. The n is R of X tilde of group G and major mu tilde, and the action is T tilde. That's the G alone. That is your cross product, that the N, non-commutative flow. And G portion and S portion, that the theta S portion, is precisely the lifting. This T, remember this action real number and the action group G commuting. Okay, it's a commuting. So you can this extend the abelian von Neumann algebra, L infinity of X tilde, the mu tilde, and you have theta S coming from TS, and that you can extend to the R, the cross, R of X tilde, mu tilde to G. That's the theta S extend to theta S. So the core is again the group measure space construction, given explicitly this way. So random derivative controls the behavior of N core. And the theta is a very simple multiplication by e to the power minus s on the space side, on the measure space side. When it goes to the function, then f following ts inverse, right? So we have a convention to write s inverse all the time. So this much is about the N, non-commutative flow. How about the center? Center of the N in this cross product is nothing but, remember action was free. Okay, the action was free, which means this abelian von Neumann algebra embedded into the construction, the factor A, is maximally abelian, right? That was the ergodicity and freeness are related, but we are decoupling. The freeness guarantees the original algebra's maximal commutativity. So the center is subalgebra of A. And as soon as you know that the A center is containing A, what is the R? The R is generated by A and group element U of group G, U of group G. And the U of the center element, the element in A is in the center if and only if that element commute with U of all of U of G. That which exactly means that C is precisely fixed point algebra under group G. Right, G, the fixed point. What is a fixed point? Oh, well, we don't see that. All right, what is the fixed point is all those functions in A which is a constant on the orbit. Constant on the orbit. That is the necessary and sufficient condition for being fixed. So, see how you visualize, and okay. So that means that you x tilde orbit space. Function is constant on the orbit means that you can shrink each orbit to the one point. Yes?
You're saying that the cross product, the center will be exactly the fixed point.
Say again, please.
The fixed point algebra is exactly the center of the cross product?
Exactly. The reason is that A is maximally abelian. So the element in the center has to be the element of A, and which commute with all of U of G. That is exactly the criterion for being central element. So the center is being fixed, and every element has to be constant on each orbit. Then that we know that why don't we consider quotient space? That so this will be L infinity of orbits. Those are called orbit space. And the major mu goes up to the here. So this space is okay. And there is, of course, the orbit space can, yeah?
Is that x or x tilde?
X tilde. Not original x. We assume original x action G is ergodic. Yeah. So if you mod out that everything collapses, no mathematics, only function constant on the orbit, globally constant. Okay? So if you divide x tilde by G, okay, the other measure space can be very singular. In that case, the group is ergodic on that one. So if in that is the case, what exactly this is the scalar C, right? That's the 3-1. That's precisely the 3-1 case. That's the 3-1 case. That's the 3-1. And indeed, in that case, this, yeah, n doesn't have the center, it's only except scalars. And okay, now because x tilde was on R plus star cross X, and here R and group G acting jointly. Okay. If you consider the jointly, then if that is R is transitive on R star, exponential, that's all transitive on the positive real line. So the jointly, this is ergodic. It's a fixed point. It's a kill this portion, only one. We assume the action of G on X is ergodic. So this is jointly this ergodic, and you are now considering partial fixed point, only G, and then you end up with R alone. So you have the flow on the this space on C. You have C, R, theta. This is precisely flow of weights. That the center, you remember n and the fixed point on the the n and the center of n and the restriction of trace scale 1 parameter automorphism on the center becomes flow. And this flow is given by this space that x tilde mod out by G. And there are cases that this orbit space is very bad, so that it is reduced to the scalar. So the algebraically, this is a fixed point under G alone. Okay, so and if that happens, it's 3-1. Otherwise, okay, ergodic flow. Sometimes it's periodic, sometimes it's properly ergodic. Yeah.
So, what is the 3-1 case exactly? You're saying that any time
Yeah.
fixed point algebra is trivial, the cross product will be type 3-1?
Yeah. Okay. This is the description when the R is square. So you can actually work out with the example we discussed, or the type 3 case, what kind of animal pops up for those examples. Remember for instance, that the lambda affair, lambda to the power n, and the 0, and that the b, and the b was in the Roland polynomial over lambda between 0 and. Then you can put the hands on. You can really visualize. Then that case, or if you do the whole thing, then what happens is then the flow of weights becomes periodic of minus long lambda. Like that. Yeah.
Is it if and only if it is type 3-1? If and only if the
It's type 3-1, if and only if the script C reduced to the scalar. So that means n is a factor. If and only is n is a factor. Otherwise, it's either periodic or aperiodic. That's 3-0 case. And those factors coming in the mathematical physics or algebraic quantum theory expected actually 3-1, type 3-1 fundamental algebras. But since nobody yet showed the actual examples, no way to confirm it. So those factors are still in the air. The mathematical physics, those quantum field theorists or algebraic quantum field theorists are really working hard to construct non-trivial example of their model. At this point, the space-time dimension is 2, then they have very good control. And in that case, actually it's a 3-1. Okay, this much is a supplement to today's talk. Now we come to the following. Suppose you are considering countable group, discrete quantum group acting on your measure space. Okay. Now, G is countable. Discrete group acting on X measure space mu. And you assume, you take freeness away from the action. Okay, freeness away from the action. So then what happened? Okay, so each X in X, okay, you have orbit of point X. Then this is actually under G acting on here by translation G part. That is the G divided by isotropy group H sub X, which is the element in H in G such that Hx equal to X. Okay, now if you look at actually what you are considered, remember the pi alpha of A psi of X was alpha S inverse of A psi X. But what is this? This is A is in L infinity over X mu. So the actual point, this is a function in L infinity acting by multiplication in the evaluation at X. This is and indeed this is then A of maybe I write it. I'll go back to the group element. Gx acting on Hx. Okay. Okay. Now, if you suppose you have. Oh no. I'm totally. No, totally. You have a good reason. It's not this one. It has to be evaluated at G. This is alpha G inverse of A psi of G. Now, okay. Now psi of G is element in L2 X mu, isn't it? Was X mu. So this is indeed, then this is A of Gx psi of also G comma X. Okay, now I'm writing this G cross alpha G comma X. That's okay. Indeed, here it would be the G and the G dot point dot. Okay. Now, Okay, here's a Krieger's the ingenuity comes in. Okay, g dot g comma x. This is what mother is the function over each orbit. Each orbit. So instead, instead of g cross x, well, indeed, this is actually a groupoid of g hx times hx equal to gh comma h. If you define the multiplication rule by that way, it becomes groupoid. And unless this and hx unmatched product is not defined, product is undefined. So if you observe that, then why don't you consider x cross x, and inside the R sub g, which is the graph of gx, g runs g, x runs x. It is a graph. Then the function over L over gx and the translation on g, that's the ingredient for this cross product. So if you do that, all this this R, then what is happening is your Hilbert space is L2 g over x, direct integral relative to d mu of x. This is your Hilbert space on which the cross product acts. Group measure space is acting. And if you do that, now this graph is actually graph of equivalence relation. You know that the equivalence relation is a subset of the square set, and satisfies certain rule about the composition or inversing it. And then you have A, B from R to scalar. What you are having is X, Y, B, Y, Z, summing X, the Y is equivalent to X. And this only the possible, permitted pairs are in the X, Y, Y, Z on all R. Then you see this is nothing but matrix product. Matrix product on the restricted to the equivalence relation. And you are, so when you have xi, then that's the action of xi of xz. So you have the matrix acting on the space of matrix, and what is the necessary condition psi y, xy, summation relative to x integral relative to mu y finite. That's the Hilbert space condition, square integrability. And then dividing it, that's the integration xy relative to, so you write it xy, that combined summation integration is then rho yx of f of yx d mu tilde of yx. You change the order, then you end up with the absolutely continuous measure. And that's the rho. That is precisely the rho function's rho. You end up with rho. So, and then this shows, this is now telling you the von Neumann algebra we talked about, cross-product von Neumann algebra, nothing but the matrix algebra coming from equivalence relation generated by the orbit of the group. Yeah.
Can you repeat what A and B is? Can you repeat what you said about the equivalence relation?
What?
Can you repeat what you said about A and B?
Okay. Action of group G gives rise to this equivalence relation. And what's special about the RG is then the equivalence class is countable. And so you count. And then integrate over the base space. That is the measure assigned on the graph. Okay. Then the absolute continuity of the transformed measure is the same as saying you change the order, so x, y, and you sum up first component and then integrate. Now instead you sum up the second component and then integrate. This gives you equivalent measure. This is precisely the rho function, right? Because second component is group acted upon for the first component. So that the rho of gx is staying there. So it is absolute continuity is precisely translated to the d mu g is absolute continuous equivalent to d mu means summing up first component and integrate, or summing up second component integrate are the same. Or differently you change the order x, y to the y transpose. Transpose mapping on R is so transpose mapping is very simple map. So you can write it a check. So this gives leave measure plus invariant. Okay, so that's the. So if you have such a situation, then you L2 over orbit or equivalence class, and then integrate this relative to the base measure. This is the Hilbert space H, on which this cross product was acting, A cross, in the event of group G is countable. That is happening. And this one is then, if you make this construction, if we make this construction, then the diagonal element is actually that's A, diagonal element. So diagonal one is maximal abelian. No longer freeness is necessary because of this. Instead of all G, you truncated to or reduced to the orbit. So you have this L2 over the orbit and integrate. So this is now, you consider this is equivalence relation and the measure mu tilde there. And okay, this is the Krieger, it's called Krieger's construction. And once again, modular automorphism, etc., can be computed very exactly the same way, and also that goes over to the construction of a core is the same. But now, what's important is the following. When this is the graph or orbit phenomena, this one, well, we take this to be countable group, but you don't need to be the countable. Or for the equivalence relation, you don't need a group. You don't need group. What you need is, so if it is no longer the group, you have equivalence relation over the fixed point. The ability to integrate vertically and horizontally. And you need when you reverse the order, then the reversed one is absolutely continuous to the original one. That's what you need. Then if you look at the reality, the mathematical reality, you have so many phenomena of this occurring. But okay, we discussed already once canonical flow. The orbit, then each orbit is a real line, but wind it up, and then integrate over the two torus, and integrate over the real line. And if you change the reverse order, that's absolutely continuous again. And those are now you move on one step. This phenomenon is all over the place in mathematics. You have foliated manifold. And if you have foliated manifold, well, that the leaf need not be gives you good quotient space, so-called leaf space. If you have space X, foliation. And the ergodic phenomena occur, they very often occur, possibly unless you are very lucky, the most cases are indeed quotient space is not, and doesn't behave well in the mathematical point. But each leaf can carry nice L2 structure. And then you can once again generate fundamental algebra out of this gadget. So this is the fundamental algebra controlling describing entire picture and taking account of the orbit or the leaf structure as well. That is around the point of the beginning of his non-commutative geometry. That's where he started out, non-commutative geometry, motivated by that. And then if you come to this far, the equivalence relations are all over the place in mathematics. Whenever you have a motion, that's already giving you the equivalence relation there. Well, so the operator algebra is occurring very next to you. It's not far remote. It's something to put on the high up on the top of the mountain. You should bring this down to the ground. Yeah, okay.